Okay, so moving right along, we're going to pick up where we left off. So we just finished question number 6. Let's move on to question 7. Which of the following are possible termination steps in the chlorination of methane? Well, we actually looked at this reaction in detail in chapter 10. There's a whole section on the chlorination of methane. And if you remember, the chlorination of methane went something like this. You take methane plus chlorine, and you end up with methyl chloride, so CH3Cl, plus you end up forming HCl as well. Now remember, termination is when we annihilate radicals, so we just need to choose something here where we have two radicals coming together that annihilate, and so also something that has a radical from the reaction. So I see two possibilities. I see that C, we have two methyl radicals. That's definitely possible coming together. And then in D, we also have a methyl and a chlorine radical coming together. And that seems reasonable. If you look at A and B, neither of those are termination. And so the answer is C and D. So the answer is D, which is C and D. All right. There we go. So another practice of termination. Let's try number 8. This free radical chlorination of ethane can produce higher halogenation products, so dichlorinated, trichlorinated, tetrachlorinated, pentachlorinated, etc. In addition to chloroethane, how could the production of higher halogenated products be minimized? So this is something that is in the slides. We talked about it. If you were making methyl chloride, right? We talked about this last class where we said, okay, if you take methane and you add chlorine, and this is the reaction that we just talked about 3 seconds ago, okay? There's, once you form methyl chloride, that's going to be even more reactive. Then it's going to make dichloromethane, trichloromethane, chloroform, etc., and then carbon tetrachloride. So how do we minimize that? Does anybody remember? What would be the best option here? Yeah, exactly. We want to use a huge excess of methane and only a little bit of chlorine, right? And that's going to minimize the amount of polychlorination that you're going to get. There you go. Nothing more than that. All right. Number 9. I'm not wild about questions like this, but let's try it anyhow. It says, how many constitutional isomers are possible if propane is dichlorinated? So if we take propane, so let's take propane and we treat it with some chlorine, and we shine some light on it. How many possible dichlorinated products could we have? I'll just start with 4 and see where that takes me. Well, one possibility is you could have, one chlorine here and one on the next carbon. You could have one at each end. You could have one on each carbon in the middle. And then is there another possibility? Yeah, there's one more that I can see that I haven't drawn, and that's where we have both chlorines on one of the carbons on the end like that. There are no other possibilities. These are the only 4 possibilities that you can have for dichlorination. Again, I'm not wild about this kind of question because if you miss one, then you get it wrong. But it is a question that they love to ask in ACS, MCAT, all organic chemistry textbooks love these kinds of questions. And I think it does get students thinking about, what are the possible structures I could have. But anyhow, that's all they're asking for here is how many different dichlorinated compounds can I make? And the answer is 4. All right, question number 10. Predict the major product upon the radical bromination of tert-butyl cyclohexane. So if I take tert-butyl cyclohexane, so that means you've got to be able to draw tert-butyl cyclohexane. So we have a cyclohexane with a tert-butyl group on it. There we go. And we're going to treat that with bromine. And we're going to shine some light on that. And if I highlight, let's say I highlight a couple of carbons here. If I highlight this one in yellow, this one in green, this one in red, and maybe this one in blue or something like that, could anybody tell me, and it's not a trick question, where's my bromine going to go, on which carbon? Where would my bromine go? Yeah, exactly. Thanks, Sean. It's going to go where the yellow carbon is, right? It's going to go to the most substituted position. And we covered the reasons, as to why that would happen last class. So we're going to have our bromine here, and then we're going to have our tert-butyl group here. And so what would we call this compound? We'd call it 1-bromo, 1-terbutyl cyclohexane. And so the answer is A. All right, 1-bromo, 1-terbutyl cyclohexane. All right, there we go. Let's move on to the next one. Predict the major product of the following reaction. I know you could do this one probably in your sleep, but let's just review it anyway. So we're putting bromine and light to this thing, this compound. If I highlight this, well, jeepers, that's too much. If I highlight this carbon in yellow, if I highlight this carbon in red, this one in green, and maybe this one in blue, could anybody tell me where is the bromine going to go? And it's not a trick question. Yeah, it's going to go in the red carbon. It's the most substituted position. And so we would end up with this compound that looks a little something like that. All right, so we get 2-bromo, 2-methylbutane is what you would get in that case. All right, let's see here. Which of the following is the correct name for the major product of the following reaction? I have a feeling that they are trying to trick us with this problem because you're starting out with a chiral compound, aren't you? Right, this molecule has, this is achiral, my mistake, because this is an ethyl, this is an ethyl. So this is not a chiral center. Oops, not a chiral center. But we know that the first step that's going to happen is there's going to be a hydrogen abstraction, right? After the initiation, which is the homolytic cleavage of the 2 bromines. Then the bromine radical, right, is going to do the hydrogen abstraction, which is going to look like this, and then this, and then this, okay? So we're going to end up forming the radical. So let's draw the resultant radical, which looks like this, okay? So there's our radical. And now we're going to do the halogen abstraction. So what's going to happen is this radical is going to react with a molecule of bromine, like this. So we end up forming a bond, and we end up putting a bromine right here, okay? Now, you don't have to draw the compound that way. I'm not wild with the way it's drawn. I would draw it like this: 1, 2, 3, 4, 5, right? And that way you can clearly see it's 3-bromo, 3-methylpentane, right? And there's no chiral center in the molecule. There was no chiral center to begin with. But you do, find some utility in this question, in that it gives you a chance to practice the hydrogen abstraction and then the halogen abstraction. So halogen abstraction. A little practice in the mechanism here, which is never a bad thing. All right, give me a thumbs up if you're with me on that one. Any questions about that one? Okay, it kind of had me tricked at the beginning. I didn't look at the question close enough. I didn't realize it wasn't a chiral center at first glance, but then we figured out it wasn't a chiral center and moved on from there. All right, here's another one. Predict the major product of the following reaction. Well, this one is actually kind of an interesting problem because there's no differentiation between the carbons that I have in red and the carbons that I'm highlighting in blue, are there? If you were to form a radical at any of those carbons, the 2 carbons in red or the 2 carbons in blue, you end up with a secondary radical. There's no place to make a tertiary radical on here. So there'd be no differentiation between the 2 radicals in terms of their stability, right? So if we were to make the radical here, or if we made the radical here, either way, those are equal in terms of their stability. So we'll put here both are secondary. So again, no discrimination here. And so the one that's in red, that's going to give you compound B, right? And then the one that's in blue, once that does the halogen abstraction, that's going to give you compound A, right? You're not going to get compound C because that would come from a primary radical, and D is just plain wrong. I mean, you lost a carbon in that one. So the answer would be A and B. So the answer is A, which is you would get a mixture of both A and B. Good question. I like that question. All right, let's move on to number 14. Predict the major product of the following reaction. Again, we're treating this with bromine and light. And don't be fooled just by the fact that there's a bromine on there. Just ignore that, right? You're looking for the weakest carbon-hydrogen bond on here. So if I was to put, you know, the proton in here in blue, and let's say I put a proton in here in red, and let's say I put a proton here in green. This is not a trick question. Where is the new bromine going to be installed? At which position? Exactly, the blue, right? Because after you do the hydrogen abstraction, you're going to form a radical there. But I think we should draw the radical because we do have a chiral center here, and we're going to destroy that chirality, right, Sarah, when we make the, or Kiana and Sarah, when we make the radical. So let's just draw it out here. And so we're going to annihilate or destroy that chiral center, but we haven't touched this chiral center whatsoever. And so now, once the halogen abstraction occurs, so I'll just put here bromine abstraction, halogen abstraction. What happens is that the halogen, the bromine, can come in from either face of the molecule. There's going to be no discrimination, or there actually would be some, but not enough for us to worry about it. So you're going to have the methyl coming out, the bromine in the back. And of course, we don't touch this chiral center. That one remains unchanged. And then if we just copy and paste this, so let me just do that quickly. We would end up with this guy here. And now I just switch the bromine over to this position here. Could anybody tell me the relationship between these two compounds? What would the relationship be between these two compounds? One stereocenter remained the same, but the other one is inverted. Exactly. Yes, these are diastereomers. Diastereomers. All right. There we go. The next one. All right. What reagents would you use to do this reaction? Well, you probably noticed that we're doing a bromination, but it's at the at an allylic position. So this is an allylic bromination. So I'll do blue here. Allylic bromination. All right, and if we want to do an allylic bromination, does anybody remember which one of these reagents would be the best choice? Yeah, the answer is D. So we'll put here NBS. NBS is best choice since we avoid addition to pi bond. So you don't get any addition to the pi bond, and so yes, the best idea is to use N-bromosuccinimide and to cook it up. All right, let's move on to the next one. Let's see what we got here. Question number 16. Oh boy, it says compound A has a molecular formula C9H20. Compound A produces exactly 3 constitutional isomers upon monochlorination and 1 major constitutional isomer upon monobromination. Which of the following are the possible structures of A? Oh, good gravy. All right. So we're going to get 3 constitutional isomers from monochlorination. Let's do that part first. Okay, so if you were to treat any of these molecules of chlorine, where are the possible places that it can chlorinate? Well, on the first one, it could chlorinate here, which is identical to here. It could chlorinate here, which is identical to here. It could chlorinate here, which is identical to here. And then it could also chlorinate here, which is identical to here. So that's a total of 4 different places that chlorination could occur. All right, let's try the same exercise in the next one. It could go here. That's 1. It could go here. That's 2. It could go here. That's 3. It could go on either of these. That's 4. And then here is 5. So that one's not a good one either. You can see that 3 definitely isn't the right answer, is it? We could chlorinate here. We could chlorinate here. We could chlorinate here. We could chlorinate here. And I'll use my black pen. We could chlorinate at these positions. Okay, so that one also you have 1, 2, 3, 4, 5 possibilities. So for this one, there's 4 places. This one has 5, and this one has 5. Let's keep going. We're looking for 3. Okay, if we go to the next one, which is also not the right answer, we have 1 place here. We have another place here. Oh, sugar, those aren't equivalent, are they? Jeepers, I made a mistake. So we have this place. It's even worse than I thought. We have this place. We have this place, right? Because this is an ethyl and this is a propyl. So this one has way too many places. It's got, let me count, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's got 9 different places that you can chlorinate. What about number 5? Did anybody figure out how many places you could chlorinate on this guy? Because there is a plane of symmetry running through the molecule like this. Big old plane of symmetry on this. So that means that all 4 of these methyl groups are chemically equivalent. These 2 methynes are chemically equivalent. You cannot do anything with this carbon because it has no hydrogens. And then you've got these 2 methyl groups here. And so the answer, or at least one of the answers, is number 5. There's 3 places that you can chlorinate. And you can see that there's no symmetry in number 6. And so 6 has a total of, you've got these. So you've got 1, 2, 3, 4, 5, 6, 7, 8. You've got 8 different places you can chlorinate here. And so the answer is number 5. I just want to ask my students, now that you see it done, does everybody understand what's going on here, how I identified? All right, so the best thing to do is look for symmetry. And I'm sure that you guys could probably answer this faster than I just solved it. But just to kind of show you the thought process to go through that one. All right, now we haven't even talked about the second part, which is one major constitutional isomer. So if we were to take 3, so let me redraw this nifty compound here. If we were to take 3, and if we were to treat it with bromine and light, there's one major place that it would brominate, right? Could anybody identify the carbon just using the colors that I used? The colors that I used here? Yeah, it's going to go with the red position, right? Because that would produce a tertiary radical. Exactly. And so you'd end up with this compound as your major product. Anyhow, kind of a fun question, that one, if that's your idea of fun. Anyhow, let's move on to question number 17. This one is just an allylic bromination, right? So NBS, remember that NBS does allylic bromination. But remember that when we form the radical does participate in resonance. And so we want to draw both of the resonance contributors. So what we're going to do then is we're going to say, okay, when you form the bromine radical with your NBS, it's going to do a hydrogen abstraction. It's going to pull off this hydrogen because that's going to make a tertiary allylic radical. So let's draw the mechanism for that. So I'm just going to draw it like this, okay? And let's draw the radical that you would get from that. So it's going to look a little something like this, okay? So now we're going to draw the resonance form, which looks like this, okay? Let's draw that guy, which looks something like this. There we go. And so bromination can occur at both of these positions, all right? So bromination can occur at both of these positions. So what we're going to do is we're going to put an arrow down here, and we're going to put an arrow down here. And after the halogen abstraction, right, you're going to put a bromine at that position, okay, here. And then you're also going to put a bromine here at this position. So these are the two, these are the 2 possible isomers that you could get. Everybody okay with that? Is anybody not okay with it? So we get this product, and we also get this product. And I had a student ask me, would the one on the left be formed in a greater amount? Probably, because that radical would be more stable. It's tertiary allylic versus the other one, which is primary allylic. But those are still the major products of the reaction. All right, let's move on to number 18. Which intermediate leads to the major product for the reaction of 2-methyl-2-butene with hydrogen bromide and hydrogen peroxide? So first, let's start it by drawing 2-methyl-2-butene. So if we draw 2-butene, it looks something like this, and then we put a 2-methyl here. And so if we react that with hydrogen bromide and an organic peroxides like this, is this going to give us Markov-Nikov addition or anti-Markov-Nikov addition? Exactly. So this is going to give us, we'll put here anti-Markov-Nikov addition, just like that. So what's going to happen is the bromine is going to add, once you form the bromine radical, in such a way that you're going to form the most stable radical. So it's asking us about the intermediate. So, if we draw just a bromine radical, if I highlight, I'm going to ask you a question. If I highlight this carbon in yellow and this carbon in red, which one is the bromine going to add to? And it's not a trick question. It's going to add to the carbon in red, exactly. So let's see here. So it's going to look a little something like this, okay? And then we're going to form this radical. So this is the intermediate that we're going to form. It's going to look like this, okay? And this is the intermediate, and this is number 2. So that's the exact same thing that I drew there. All right, so the answer for this one is B. All right, predict the product of the following reaction. Well, the next one is just a Markovnikov addition, isn't it? We're taking 1-methylcyclohexene and we're treating it with HBr. This gives you another opportunity to practice your Markovnikov addition, right? The rich get richer. And so this carbon, which possesses 1 hydrogen, is going to take the hydrogen. So we're going to draw the carbocation that results. So we end up with this carbocation that is not going to undergo any rearrangement whatsoever. And so now our bromide that we produced in the first step is going to act as a nucleophile. It's going to come in and attack here. And we end up with 1-bromo, 1-methyl cyclohexane as our product. All right, so make sure you review your Markovnikov addition as well, and make sure you can draw the mechanism that's drawn here, right? Very important that you're able to draw the mechanism of Markovnikov addition of an acid across a double bond. Okay, next one involves dihydroxylation. Wow, we haven't seen this since chapter 8. But anyhow, it says propose an efficient sequence of reactions to accomplish the following transformation. Well, just in terms of retrosynthesis, if we want to make a transdiol, we know that we have to add the hydroxyls via anti-addition. And there's only one way that we know how to do that, and that's starting with the alkene and using MCPBA followed by aqueous acid. Now, there's a couple of possibilities that show us MCPBA with aqueous acid, so we'll be more concerned about that later. But one thing that I want to really make sure that you understand before you leave lecture today is that pay very close attention to my words. Whenever you're asked any kind of question that's a synthesis from now on, and if they give you any kind of molecule that's just an alkane or a cycloalkane, the only possibility for the first step is bromination. That's it. Of course, you could use chlorination in this case, but we almost always use bromination. So the only possibility is to do a halogenation. I repeat, if you have an alkane or a cycloalkane, the only possible reaction that you can do, even to the end of organic 2, is to brominate it. So that means that we can eliminate the first 2 answers because bromination is not the first step. So let's draw what you would get after you brominate this compound, cyclopentane. So if we take this and we treat it with bromine and light, we end up with bromocyclopentane. Now, if we want to make that or convert that into cyclopentene, we have to do a deprotonation. So what's going to be our best choice here? Our best choice is not going to be C because it starts out with bromine and light, but then it has sodium hydroxide and DMSO. That's going to do an SN2 reaction. We don't want to do that. So you can see that the next 2, D and E, they both have potassium T-butoxide. So if we treat that with a hindered base, it's going to alleviate, or not alleviate, it's going to eliminate the possibility of any substitution. You're only going to get elimination, and that is going to give you the cyclopentene that you're looking for. So we know that it's either D or E. Now, again, I've already covered the fact that it must be E because the last 2 steps are to use MCPBA. So MCPBA, which is going to make the epoxide. And let's just say it's going down like this. And then when you treat that with aqueous acid, that pops the ring open, okay? And you end up with 1 hydroxyl going down and the other hydroxyl group coming up like this. You end up with a transdiol, plus you also get the enantiomer. So the correct answer here is E. Is everybody with me on that one? Any questions about that synthesis? A very important synthesis, right? It incorporates right? This is a reaction we learned in chapter 10. This is a reaction that we covered in chapter 7. And the last one is a reaction that we covered in chapter 8. So you can see how you really have to have a mastery of all of the different chapters in order to really be proficient in chapter 10. Let's move on. Question 21, of the four choices shown, which is likely to be the major product of the reaction shown below? So we have anti-Markovnikov conditions here, and then we have this conjugated double bond here. So, if we're doing the opposite of the rich getting richer, well, let me ask you a question. There's two double bonds in here. I'm going to put this double bond, I'll circle it in blue, and then I'll put this double bond in a red circle. Okay. Now, one of those double bonds has no meaning if we were to discuss Markovnikov and anti-Markovnikov. Could anybody tell me which one of these double bonds is not pertinent for Markovnikov and anti-Markovnikov? Okay, so the one in blue is definitely relevant for Markovnikov and anti-Mark, right? Because this carbon has two hydrogens. But the one in red, both of the carbons in the double bond have one hydrogen. And so for the double bond in red, there's no relevance for Markovnikov or anti-Markovnikov. It doesn't exist, okay? So not only that, so that tells us why we're going to add to the bond in blue. But another thing is that if you do the addition of the bromine radical to the one in blue, or the one that I had in blue, like this, okay? So if we form a radical like this, check out the radical that we end up with. We end up with this radical, which looks like this. So we have our bromine, we broke that double bond. Here's our radical, and you can see that it is tertiary allylic. So the radical that you end up producing is tertiary allylic. So it is very, very stable. So this is going to be one of the intermediate, or the intermediate that we form. And then after you do the hydrogen abstraction, so after you add the hydrogen, you're going to end up making compound number 1 is the compound you're going to end up with. There you go. This is kind of an interesting problem because you really have to understand the mechanism of the addition of HBr and peroxides in order to get the right answer here. All right. Even if you didn't know that, you would know that it would have to add to the double bond that I had highlighted in red, because that's the only one where there's any kind of relevance for Markovnikov and anti-Markovnikov. Number 22, propose an efficient synthesis of acetone from propane. So you have to know what acetone and propane are. Well, I know you all know what propane is. It's this here. Acetone is nail polish remover. Okay. So acetone, you can also call acetone, can also be called propanone. Nobody calls it that, but that would be a systematic name for it. Anyhow, let's take a look here. If we wanted to do a synthesis here, what's the only option that we have for the first step? The only thing that we could do is to add bromine and light, right? That's our only possibility here. Now, if we do that, that's going to install a bromine here.